Hey, what's up? All right, welcome back, everyone. How are y'all doing? Good? Good? Did you have a relaxing break? No? Oh, I'm sorry. I didn't either. I don't know if that makes you feel better. Did you at least get stuff done, maybe then? Do you have a productive break? No? Oh, all right. Well, that sucks. Try to make sure you are taking care of yourselves. Make sure you are getting sleep and eating, because yeah, we're at the second half of the semester, so we want to make sure that we're hanging in there, because usually the second half semester usually gets harder in pretty much every class. So you want to make sure that you're staying on top of things, predominantly your health, because you need your body, you need your brain in order to be able to learn things and then apply it. So you want to make sure that you are taking care of yourselves. All right. With being in the middle of the semester, please do fill out the mid-semester feedback. I'd posted an announcement right at the beginning of break, and then asked that it was completed during break. Most of you didn't. That's fine. I understand. It was break. But it is really important to me to make sure that this class is helpful and that the way that I'm presenting the material is working for you, and to find out if there's anything that can be doing better. So any changes that you request that I can reasonably implement, I will implement. So please do fill out the mid-semester feedback survey. For most students, they were generally spending about like 3 minutes on it. I've had students in the past be able to do it in like less than a minute. I've had other students spend like hours on it. You do whatever amount of time you can provide. So it's a lot of just, strongly agree, strongly disagree, those kind of rankings, and then a couple open-ended that you can write however much you want. And that's usually where students would spend very little or a lot of time on writing everything out. But yeah, please do fill it out, and then I will summarize the results and report it back to you to let you know what changes are going to be implemented and address some concerns and explain why I can't make some changes. Cool. All right, does anyone have any questions? Yeah. Oh. Yeah. All right. Should I turn it off and on again and see if that fixes it? Thank you for pointing that out. Yeah. I saw something was projected. I just assumed it was projecting correctly. That was not a fair assumption. Well, it looks more centered initially. That's exciting. Yeah. Okay. We can actually see everything. Yes. Cool. Thank you. All right. Any other questions or comments? All right. So usually after any break, students forget everything that had happened prior to said break, even if that break was only 2 days. So let's start by, I thought that actually where we left off is a really good kind of segue in that we can summarize them. So first of all, what are the 4 mechanisms that we learned? SN1, SN2, E1, E2. Beautiful. So we have substitution elimination. So if we're doing substitution, our reagent is acting as a nucleophile. That means that we are attacking that carbon, right? And that's the big difference, is that for substitution, we attack the carbon. In elimination, our reagent is a base. The base is going to attack the hydrogen. So if you're doing elimination, you attack a hydrogen. If you're doing substitution, you attack the carbon. Your reagents look very similar. It's just going to be determining, do they prefer the carbon or do they prefer the hydrogen? And that's going to be our big tug of war difference. All right, SN2 is how many steps? 1 step. SN2, 1 step. Why is it SN2? What does that 2 mean? There are 2 reagents in the rate determining step. So your nucleophile and your substrate control your rate. That's what it's saying. So that nucleophile and the electrophile both are going to react together. It is nucleophile attacks as the leaving group leaves. It's happening simultaneously. So SN1 is how many steps? 2. SN1, 2 steps. So for SN1, what is the 1 indicating? Only the substrate is involved in the rate determining step. Only that electrophile controls your rate. We don't care about the quality of the nucleophile in SN1. All we care about is our electrophile, our substrate. So what we really care about is making that carbocation. SN1 is all about that carbocation stability. That's the big deal for SN1. SN2's big deal, because everything has to come together, is going to be sterics. SN2, you got to be able to get at that alpha carbon. You got to be able to get at the carbon that has the leaving group, because you have to do that backside attack, where your nucleophile comes in, pushes the leaving group out, because that's where that accessible sigma star is located, right? Hopefully all these words are like slowly ringing bells. So that backside attack is what gives us our inversion of stereochemistry. So that's what flips it. Right? So we had said for SN2, you must have an sp3 hybridized carbon, and you want it to be primary or secondary because it doesn't have a lot of sterically encumberment, right? It's easy to access your primary leaving group or your secondary leaving group. You want a strong nucleophile, right? So you wanted that nucleophile only category to favor SN2. You wanted it to generally be a weak base because you want to make sure that it's just going to go after that carbon to do the substitution. If it is both a strong nucleophile and strong base, then you want lower temperatures, because remember, temperature is what helps us pick between S and E, between substitution and elimination. Solvent picks between 1 and 2, because your solvent in SN2 is that aprotic. The aprotic was favored because that's what let you have a weaker solvent shell. In aprotic solvents, you don't really form a strong solvent shell. That solvent shell is that bubble around your nucleophile. So you don't want the bubble around the nucleophile. That's what aprotic does. Aprotic says there's no real bubble. Your nucleophile can easily access your electrophile. For SN1, because I don't care about the quality of my nucleophile, I'm cool with polar protic, because polar protic will form the bubble that weakens my nucleophile, but I don't care because the nucleophile isn't in the rate determining step. Only the electrophile is, only the substrate is. That's what the 1 is telling me. For SN1, we still must also be sp3 hybridized. That carbon must be sp3 because that's where we're going to get our stable carbocations. And again, we want that secondary or tertiary to help stabilize the carbocation, because the more substituted it is, the more stable your carbocation is. For SN1, it did also favor our strong nucleophile, But if you have a weak nucleophile, weak base, then that was also going to be lower temperatures, because again, low temperatures favored substitution, right? We said room temperature and heat favored elimination, and room temperature is assumed if nothing is written. So if you don't see cold or hot, you assume it's room temperature. Room temperature is going to favor elimination, is what we said. It's just a general making things easy. All right. So for our SN2, those key factors again, is that it is one step. It is concerted. You see the new substitution at the alpha carbon, meaning your nucleophile is attached to the exact carbon that had the leaving group. It is directly replacing it, right? That nucleophile directly attacks the carbon that kicks out the leaving group. So your nucleophile, the new substitution, is at that alpha carbon. You get inversion of stereochemistry, but we're always going to watch out because that R and S assignment, remember, that's arbitrary. That is that Coningal-Prelog. So you're only going to go from R to S or S to R if your nucleophile and your leaving group are the same priority level. So if they're not the same priority level, all bets are off. Coningal-Prelog said that it's just based on the atomic number. Higher atomic number, higher priority, and that was how we did our arbitrary rankings, right? So it's always going to have inversion. You always have inversion because that's the only way you can get at that sigma star is from the back side. So you come in, you push out the leaving group. That's your only option. SN2 requires that. So the inversion always occurs 100% with SN2. It's just the R and S label might not flip because it depends on the priority ranking of your nucleophile versus your leaving group. For SN1, we had said that that was 2 steps. So it was leaving group leaves, then nucleophile attacks. And we got to make sure that we watch out for carbocation rearrangements. So the new substitution generally will be at the alpha carbon, but watch out for carbocation rearrangements. If you see the new substitution at a carbon other than where your leaving group was located, you had to do SN1. That's the only way you can get your nucleophile attached to a carbon other than the one that directly had the leaving group, is if you had a carbocation rearrangement. That hydride shift or the alkyl shift, that was going to lead to a more stable carbocation. Remembering that what gives us a more stable carbocation is that resonance, induction, hyperconjugation. Resonance being the strongest factor. If you can get resonance, beautiful. That is going to be way more stable. Without resonance, then we're looking at tertiary is more stable than secondary, which is more stable than primary. That's our general ranking. For SN1, we see loss of stereochemistry because we go through that planar sp2 hybridized intermediate, that planar carbocation. You can attack from the top or the bottom, from the front or the back. So since you can come from either side, you're going to get a mixture of wedge and dash. So if you see racemization, you did SN1. Racemization, SN1. All right. Do we have any questions about our SM1 or SN2? Trying to remember those. Cool. All right. So then we looked at our eliminations. And with our eliminations, we had, again, E2 and E1. We said E2 is typically in competition with SN2, so the concerted mechanisms compete. And our E1 is in competition with SN1. Our stepwise reactions compete. So E2, just like SN2, is one step. So E2 is one step. That 2 relates to your, well, it's not a nucleophile now, we call it a base, and the substrate being the 2 things in the rate determining step. They have to all come together because it's all going to happen in one step. The important thing to note for E2 is E2 can happen with pretty much any substrate. So it can happen with our sp3 primary, secondary, or tertiary, and it can also happen on sp2. E2 is the only reaction that works on a double bond. We are not going to be able to make a carbocation on a double bond. you cannot do SN2 on a double bond. The carbon leaving group bond is too strong, and it's harder to access that sigma star when you're on the sp2 hybridized carbon. So SN2 will never happen on sp2, had to be sp3. E2 is the only reaction that can happen on sp2. And the importance of that is that's gonna be how we make our alkynes. That's how we're gonna make our triple bonds. For E2, we had said that sp3 was favored. That was faster because we were looking at the number of beta hydrogens. E2 can happen on any of them, but because I'm not attacking the alpha carbon, sterics now doesn't matter. I'm not trying to get at the carbon with the leaving group. I attack next door. I attack the beta hydrogen. I attack next door. So if I have more beta hydrogens, which is usually going to be seen if you're a tertiary, then it's going to be faster. The more beta hydrogens, the faster the reaction. That's why tertiary is now favored. So for E2, we're typically looking for our strong base, weak nucleophile. I just want it to prefer the hydrogen. I just want it to be a strong base. If you have higher temperatures or room temperature, it can be strong. It can be a strong nucleophile and a strong base. Again, because we're trying to have this happen all in one step, I need my base to be able to get at that proton all in one go. Aprotic is typically favored, although solvent effects are less significant in our elimination reactions. So solvents aren't as great of a factor, but if you have to pick, aprotic is going to be the deciding factor between E1 versus E2. For our E2 reaction, we were attacking that beta carbon, that hydrogen attached to the carbon next door, directly next door to the carbon with the leaving group. For E2, we had issues of our regiochemistry and our stereochemistry. So for regiochemistry, that was saying, do I attack the left or the right? Right? That was the regio. Which region? Left or right? That is going to be based on our base, so our sterics. So that was looking at our Zaitsev versus Hoffman. Which one was more stable, Zaitsev or Hoffman? Zaitsev, good. So the more stable was the Zaitsev because it was more substituted. Hoffman was the less stable, less substituted. So we picked it based on the sterics of our base. So we did Zaitsev if you were a non-bulky base. Essentially, if you were small enough to take the substituted hydrogen, then you would. Because that was that thermodynamic favored product, you would lead to the more stable product. Hoffman, we said that we were going to do that if we were a bulky base. So then if you're really big, you're just going to take from the side where you have more hydrogens. You have less sterics. Where it's easier to access, then you'll just go there. So that is your Hoffman product. Our stereochemistry is that E versus Z. So the regiochemistry is Zaitsev versus Hoffman. Stereochemistry, that was the E versus Z. Our stereochemistry was based entirely off of the fact that antiperiplanar geometry is required. You must take the hydrogen that is 180 degrees from your leaving group. It must come from that opposite side because again, that's where that sigma star is accessible. So you had to come from the hydrogen that is 180 degrees your leaving group. That's what actually let you do your E2. E2 must have antiperiplanar alignment. It will not occur without antiperiplanar alignment. It is a requirement because of the orbitals. So with E2, you could see either E or Z, cis or trans. You can see either, or I guess trans or cis, either stereochemistry. And it all was based on making sure you get the antiperiplanar alignment. So if you had multiple beta hydrogens, so you have multiple hydrogens on the carbon. So consider your regiochemistry first. Pick the left or the right. If you're taking it from the left-hand side, and you go, okay, are there more than one hydrogen attached to that carbon? Pick the left or the right side first, and then say, do I have more than one hydrogen on that carbon? That's what I mean by multiple beta hydrogens. Do you have multiple hydrogens on that carbon that you're taking from? If yes, you're just going to make the more stable alkene. You're going to make E over Z. If you only have one beta hydrogen, that's when we had to look at the Newman, because it could have been E or Z. So you had to look at the Newman projection to ensure that you are antiperiplanar, and then look at where the groups are. Are they on opposite sides or the same side? Where are the big groups located? Because you do not have a choice with E2. You must have your hydrogen 180 degrees from your leaving group. That's it. That's your only option. Otherwise, the reaction does not occur. Right. For E1, we again had to go back to sp3 hybridized because we're looking at the carbocation stability. So that was tertiary, was where we were really only seeing E1, was with tertiary. It can happen with secondary, but it's really pretty much only going to happen with tertiary. And we're really looking at higher temperatures with a weak nucleophile, weak base is really the only times we're looking for E1. E1 is going to typically be favored in a polar protic solvent. E1, 2 steps, because it's leaving group leaves, then base attacks is our E1. Leaving group leaves first. So leaving group leaves, then base attacks is the 2 steps. So we're looking again at elimination at the beta carbon, but again, watch out for carbocation rearrangements, because you must make the carbocation first, and so then you must make the most stable carbocation before anything else can happen. So it's leaving group leaves, then check your carbocation, then base deprotonates. For E1, because we go through that carbocation, that planar intermediate, Zatsev, regiochemistry, and E, stereochemistry, are going to be the major products. Those are the products that we're seeing, is the Zatsev, the most substituted, most stable alkene, E, where our big groups are as far apart as possible. That's going to be for E1, because we're going through that carbocation intermediate, we're going to be able to pick the more stable alkene. That's the one that's going to form. And again, for E1, because the base isn't in the rate determining step, the identity of the base doesn't matter. If it's bulky, if it's small, non-bulky, doesn't matter. You're always going to make Zatsev, you're always going to make E, regardless of the size of your base, because the base isn't a part of the rate determining step. All right. Do you have any questions about elimination? Okay. So let's see some examples putting this into practice. Remember that our general process is we look at our reagent first, then we look at our substrate, and then if we need to, we'll consider the additional considerations of solvent or temperature. Only if we have to. We're not going to look at them first. We look at them last. Don't get distracted by that, because a lot of students will get tripped up. And then once we do that, then we'll look at our regiochemistry rules and our stereochemistry. So that's the order that we're going to do, solvent or temperature, I should say. Then we'll do regiochemistry and then stereochemistry. Okay. So when we look at this, we need to look at our molecules. So remind me, what is OTS? It's tosylate. So what is that? What's it act as? It's a leaving group. That's one of our really good leaving groups. It's one of those sulfonates. So it's OTS is actually that OS double bond O, and then you get benzene with a methyl. That's that OTS is that thing. It is an exceptional leaving group. So what does that tell me about that molecule on the left? Is it my nucleophile or electrophile? The electrophile. The leaving group is on the electrophile. All right, so then we're going to try to find our nucleophile. So what is going to be my nucleophile? That NaCl, that chloride, is going to be my nucleophile because remember, sodium is a metal. Metals dissociate, well, it's metal and a non-metal makes an ionic bond. Ions can dissociate and they separate into Na plus and Cl minus. So that Cl minus has a lot of electron density. It is really negatively charged. Well, it is negatively charged. And so then that's going to make that my nucleophile. All right. What does DMSO act as? Solvent. It is that aprotic solvent. DMSO is that dimethyl sulfoxide. So it's that thing. It's that ketone except that sulfur replaces the carbon, is DMSO. So it's an aprotic solvent. Okay, so we figured out what each of the reagents are going to act as. Each of the molecules are going to act as. So we said reagent. So the reagent is going to be that chloride because we're looking for the nucleophile or base when we're identifying our reagent. So chloride, how is that going to behave? Strong nucleophile, is it going to be a base? No, why not? Because it's the conjugate base of one of my strong acids. Remember, HCl is one of the strong acids. So this is a nucleophile only, or you could say strong nucleophile, weak base. So because it is the conjugate base of a strong acid. So it's not going to take that proton back. So what is the conclusion that I get from the fact that it's a nucleophile only? Which mechanisms am I going to go through? SM1 or SN2? Because it's not a base, it can't do elimination. It's going to act as a nucleophile, so it's going to attack a carbon. So that means my options are now going to be SM1 or SN2. So when we looked at that last table, if you're using this table, we would see, chloride is here. That puts it in the nucleophile only. That's how I figured out SM1 or SN2, right? That's how I use that table. Okay, so now I look at my substrate. For my substrate, is that going to be primary, secondary, tertiary? Secondary, how do you know? It's attached to 2 carbons. So you go leaving group, alpha carbon. Alpha is the one that is directly connected to the leaving group. And I say, how many carbons are attached to it? 2. So it is a secondary leaving group. All right, so what does that tell me? Still SM1 or SN2. That didn't actually really tell me anything. All that tells me is I got to look at my solvent or my temperature. All right, if I'm picking between stepwise or concerted, if I'm picking between 1 or 2, what do I look at? Do I look at solvent or temperature? Solvent. Temperature picks between the letters, between E and S. Solvent picks between if you're stepwise or concerted. So that's between 1 or 2. So we're going to look at our solvent. I don't actually care about the fact that it's room temperature. So then I look at my solvent. My solvent was DMSO. You already told me that that is an aprotic solvent. So what is the conclusion that I get from that? SN2, beautiful. So that means I'm going to be doing an SN2 reaction. So what was the regiochemistry of the SN2? Where did my nucleophile end up? On the alpha carbon, right? Because its nucleophile attacks as leaving group leaves. So you're going to get your nucleophile at the alpha carbon, meaning your nucleophile has to be attached to the same carbon where your leaving group is located. So you're going to like cross out the leaving group, put on the nucleophile. What is the stereochemistry of SN2? Inversion. So that means that if we were a wedge, we become a dash. If we were a dash, we become a wedge, because we're going to invert our stereochemistry. So now we look at our molecule and we're like, all right, cool. So I put all of the carbons exactly as they are because they come along for the ride. And then my leaving group is going to leave as that nucleophile attacks. So at that alpha carbon is where I get the nucleophile and I see inversion of stereochemistry, so it's on a dash. My mechanism, because it all has to happen in one step, is just chloride attacks in, and that kicks out my OTS. Cool. Does that process make sense? Does anyone have any questions about it? All right, sweet. Okay. Then I want you to try the next one. Whenever you have identified the mechanism, go ahead and vote on it. They'll let me know when you're done. All right, I think we have most people that are here. So now that you've picked one, now I want you to talk to someone next to you. See if you got the same answer and if you can try to convince yourselves. And then if you come up with a different answer, feel free to like change your answer in Top Hat. I'll give you about 2 minutes to converse. All right, 10 seconds. All right, let's see what all we came to. Excellent, good. E2 is the correct answer. All right, so let's talk about why. All right, so this is going to be an E2 reaction. So we go through our process. We look at our reagent. Our reagent is going to be that tert butoxide, OTBU minus. So that is a strong base, and it is not a nucleophile. So we would say weak nucleophile because it's a non-nucleophile, because it is so bulky. So that is going to be E1 or E2. The fact that it is secondary is my substrate, because I go to my alpha carbon, there are 2 carbons attached. Secondary leaving group tells me E2. That's where I'm like, all right, cool. I have a really strong base, and I have quite a few beta hydrogens to take from. E2 is going to be very fast. So right away, like, I don't even need to look at anything else. I know I'm doing an E2 reaction because it was strong base and then secondary leaving group. So that's why we're going to consider solvent last. In this case, solvent wasn't given, but a reasonable solvent to assume, especially for an elimination reaction, is going to be the conjugate acid of your base. So reasonable solvents would be something like the tert butanol, or it's usually written actually, the conjugate acid is typically a solvent for like any of the times you get the O minus. Because if you're, especially with elimination, if you're going to be making that OH bond anyway, like this is gonna deprotonate, so you're gonna end up with this protonated in the end, then that's gonna be a reasonable solvent to have because you're gonna make it in solution, so you know it's all gonna work in solution together. So even though there was no solvent written, which is usually a good indicator that you didn't need it, was because I didn't give it to you. But if, say, on an exam, you needed to provide a solvent, a reasonable solvent would have been the conjugate acid. Just if you had to pick one, that would be a good one to pick. Or because it's E2, you could also list any aprotic solvent. So it would either be the conjugate acid of that base or any aprotic solvent would have been perfect. Those would have been the accepted answers if you had to provide a solvent. Cool. So solvent, we didn't actually worry about because we already figured out what our reaction was. We knew it was going to be an elimination, an E2 reaction. Dope. All right, then we consider our regiochemistry. The regiochemistry is that it is a bulky base. That was one of our bulky bases. Remember our 3, I think were how many I gave you? Were the tert butoxide. So that TBU is what makes it bulky. Then also having your diethylamine diisopropylamine or triethylamine. Those were our 3 bulky bases. Bulky base tells me I'm going to do the Hoffman product. That it's going to be my less substituted alkene. So that means I'm going to take it from the top. Because when I compare this, I have 3 beta hydrogens here. Because remember, alpha is the one that is directly connected to the leaving group. I don't take that. I don't play with that carbon. I play next door because I'm doing elimination. I go next door. So I have either 3 hydrogens across the top, or I have 2 hydrogens to the left. Because I'm a bulky base and I have a choice, I'm going to take from the side where there are more to take from. So this is going to be my major side. I'm going to take from this side. So when I consider my stereochemistry is saying, all right, well, I have to be antiperiplanar. I don't have a choice. But I'm going to look and I see I have multiple beta hydrogens. There are multiple hydrogens on that carbon. So because there are multiple beta hydrogens on that carbon, if stereochemistry is a possibility, I'm going to take whatever hydrogen gives me the more substituted or the more stable alkene. I'm going to make the E alkene if possible. So there are multiple beta hydrogens, which tells me I'm going to do E if possible. I'm emphasizing if possible because we're going to end up with an alkene that actually has no stereochemistry here. If it was possible, you would make sure that you drew the E alkene or the trans alkene. All right, so when we look at our product then, we're like, all right, cool. So I need to end up with my double bond between the alpha and beta carbon. I'm going to lose the hydrogen that is antiperiplanar to that leaving group. So my product is that alkene. My product is pent 1-ene. Yeah, pent. That is my major product. Cool. Does that make more sense for those that didn't pick E2, or even those that did? Like, are there any questions? I guess is a better way to phrase that. Yeah. Yeah. So the actual elimination, we're going to start at that lone pair of our strong base. We're going to attack the hydrogen that is antiperiplanar, the hydrogen on the opposite side. We're going to be breaking that carbon-hydrogen bond because hydrogen can only make 1 bond. So then the electrons from that carbon-hydrogen bond are what are going to go to make that double bond between the alpha and the beta carbons. Because carbon can only have 4 bonds, and there is an implicit hydrogen there, I have to kick out the leaving group. So its base is attacking as leaving group is leaving, all in one step. Any questions about that? Yeah. So if your products are asking for the major organic, I guess I should emphasize that. Organic product, organic meaning the thing containing carbons and hydrogens, then no, you don't have to write your iodide. You don't have to include any of the inorganic byproducts. So on my mechanism questions, so if it's a predict the product, like how this is, then no, I would not expect you to write the I minus. I wouldn't expect you to write any, or even that OTS leaving group. Like I don't expect you to write any of the byproducts. I just want the major organic product, where you see all your carbons, that's what I care about. For the mechanism problems, if I'm asking you for a mechanism, I do want you to draw in all organic and inorganic products. So on mechanism problems, I want you to keep track of everything, every bond being made and broken. So in that case, I would want you to put in the I minus on a mechanism problem. Yeah. Yeah, so what you would do, if you're trying to show all byproducts, then you would need to have that tert-butanol and that I minus. And if you wanted, the K plus should actually probably also be in there. Yes. Yeah, you can combine the potassium and the iodine to make it Ki, make it ionic. Yeah. Yes. So in this case, this is not just the solvent, like it is actually being formed. So because that's a bond that you are making, yes, I want you to draw it in. In this case, it just so happens to be what we said would be a reasonable solvent. So if it is, it might happen to be a solvent, but if that's a bond you are making, yes, you must draw it in, even if it is the solvent. All very good questions. Okay. You ready? Yeah. Yeah, so in our minor products, so if I'm taking it from this side, in which case then I will have stereochemistry, my minor product is going to be where the trans is going to be the major, and then the minor of the minor would be the cis. So like here you would have stereochemistry. So because again, there are multiple beta hydrogens on the left, there were 2 hydrogens here. So then that means that if you can have stereochemistry, then that transalkene or the E-alkene would be major. So here I can have stereochemistry. Oops. So now that I can, having it be trans is better. Cis is still technically possible, but this is like, if we're trying to predict like, all right, how much do you see? This is like a 1%. I'm making up numbers. This is like 1%, this is like 9%, and this is 90%. So normally you don't even show the cis product because it's so minor. So unlikely. Cool. So normally if you're just trying to show the minor product, this is the one that I would be looking for. If you included this as well, then I wouldn't take off points, but if you showed just this one, then that would lose points. Like I would be looking for this one and then I would ignore that one. And then if you just showed this, then you would lose points because that's not a good minor product. Did that make sense? Essentially, I'd be looking for trans is the point. You technically would be right if you show some cis, but you wouldn't be answering the question of like, what is a good minor product? Good minor product would be the transalkene. Okay. Any other questions about this example? All right, we're going to do another one. Kicking it up a notch. Again, try it on your own first, and then whenever you are ready, I'm going to have you vote on top hat. Where we're picking the major product. I want to know what is the major reaction pathway? What is the major mechanism possible for this third example? All right, for the sake of time, go ahead and just guess whatever your best guess is at this point. Even if you're not 100% sure, we only have a couple minutes left in the class, so we'll just vote on whatever you think is most likely the right answer. Remember, now is the time to be wrong. If you're not sure, it's totally cool. We're going to talk about it anyway. So just do whatever your chemical intuition is telling you is the right answer. It's also totally anonymous, so if you're wrong, I'll never know that you put in the wrong answer. All right. In 3, 2, 1. I'm going to close it. Okay. All right. Excellent. So I'm really glad that what we're seeing is that we're at least recognizing it's concerted. So the majority of you are recognizing that. So like I said, this is a really hard one. So it's understandable that there's a lot of confusion. So the first thing we do is we look at our reagent. We see OH minus, hydroxide. Hydroxide is strong, strong. It's a strong base and a strong nucleophile. So that tells us it is either going to be E2 or SN2, right? That's what the strong nucleophile, strong base. Seeing an O minus right away tells me strong, strong. O minus without it being terbutoxide. So then I look at my substrate. My substrate is a secondary leaving group. So with secondary, it is going to typically be that the E2 is usually the major, but it's like, you could be E2 or SN2. We're not really sure. So then we look at our temperature. Remember, if nothing is written, we assume room temperature. Room temperature is going to be E2. So E2 is the major reaction pathway there. All right. So think about what your alkene will look like, and we'll talk about that next time. We'll look at our regiochemistry and the stereochemistry for how to get there. All right. Have a wonderful day. I do have the regraded exams. If you saw a comment in Canvas, that means your exam is ready to be taken. And everyone else, I have regraded all of them. I just haven't entered all of them into the grade book. All right, have a wonderful day. What's up?